Please welcome Benno Rice.
So yeah, after last year I thought I'd go a bit less controversial. Anyway, so I thought I'd start in good form by stealing something from Gary Bernard. Gary Bernard is the author of the WAT talk. If you haven't seen that, see that, then watch Katie's talk about explaining the WATs. But at the keynote that he gave at PyCon in Montreal a few years back, he talked about the state of knowing things, but also the state of knowing that you know them. And he put up this kind of truth table thing about whether you know something, whether you meta know it. And you know, if you know it, if you know something you know, then it's a known, it's knowledge. It's there, it's something you can use. If it's something you don't know, but you know that you don't know it, that's a known unknown. That's something you can go and find out later if you need to. That's all good. If you don't know it and you don't know that you don't know it, then it's an unknown unknown, and that's something that might come to bite you later on. But there's a row missing from this. What happens if you know something but you don't know that you know it? Gary defined that as ideology. And I think that's a pretty good definition, but tradition, I think, is also somewhat appropriate there. It's something where it's the kind of background radiation, and it's something that you just use without really questioning it. And so, to get started, So, I work for a company that makes a lot of USB devices. One of our USB devices, which is not the key that you've got in your things, it's a hardware storage module, involves a piece of software we call the connector, and it talks to it over USB. And I was wanting to rewrite that in Rust, because you do. And the problem was that at the time, the libUSB bindings for Rust were somewhat bit-rotted. And so I decided to try and implement just enough of what libUSB did in Rust itself on the three platforms that we cared about, which were Windows, Mac, and Linux. And basically, I just wanted to implement this. I want to iterate over the USB devices to find a device that matches a given vendor product tuple. I want to get the device's serial number, because sometimes we have more than one attached. We want to make sure we're attaching the right one. I want to open the device and claim interface 0. USB devices can have multiple interfaces, blah, blah, it doesn't matter. Send an echo request packet and get the response back. All good. So here, in fairly quick terms, because otherwise I'm going to blow my entire runtime on just this, is what that code looks like without any error checking or anything. Do not run this code. Windows. We start by getting a class device thing. We create an enumerator for it. We get some devices. We get interface detail, not once but twice, because the first time we're just trying to get a byte count, so we do it again. Once we've got that, then we have a device path. This is not a file system path. This is a device path. This is not /dev/something or the Windows equivalent. It's like the device tree path that you get. So that's all good. Then we open that with create file W. The W means wide or Windows or something. It means not ASCII. And that's about the only actual file operation you'll see in this whole thing, because we rapidly move on to the WinUSB API, which is the API for talking to USB devices from user space in Windows. So we create an interface handle. We get the device descriptor, which gives us the vendor and product things that we need in order to be able to tell whether we got the right one. Then we get a string descriptor. This 409 value is one you'll see a lot. That is USB speak for English. So we're getting the English serial number, not any of the other fancy serial numbers. And then we make sure it's the one we want. This is actually in UTF-16 for reasons, but whatever. So now we've got the device we want. We do a bunch of mucking around with setting pipe policies. Pipes are the things that you use to communicate with the USB device. This one tells it that we want it to send zero-length packets when necessary. This one and this one are all about just clearing the pipe to make sure that it's not going to fail on us, and then we can write data to it and read data from it. So that's not so bad. Like, I was actually pleasantly surprised by this, because it's not too bad. You've got a bit at the start where you are doing the device iteration and finding the device you're looking for, and then you've got the actual USB stuff on the other side, and that's, you know, it all flowed together pretty well. So Mac. We start by creating a dictionary, which is used for matching devices. We tell it we want to match USB devices. Then we go and find all the matching services. A service is a thing that lets you talk to a device. We iterate over these. And then we create plugin interface for service. This returns us an object that we can use to communicate with the device. This is a COM object. as in component object model. I'm not making that up. But it's for a good reason, because it lets them version the interfaces. You'll notice just above the bit I've highlighted, it says KIO USB device interface ID 650. That means version 650, which pertains to macOS 10 point something, I can't remember. So we have to call query interface, which is comm speak for actually I want this class, not the one you gave me, at which point we don't need it anymore, and we can go on and do something else with it. So now that we've got our device, we can call get device vendor and get device product. That lets us find whether we've got the one we want. Then we can call get serial number string index, which tells us where in the string table the thing is, and then we have to construct an actual request structure in order to get it, which we then send. You'll notice that there's a lot of C structure function calling here. That's all fine. Then we make sure we got the right one. And then the next fun part is we have to create interface iterator, because we have to iterate over the interfaces that the device is giving us. So this is another one of IOKit's iterators, so we're calling IO iterator next again. That construction is merely tell me what interface number you are so that I can check it. And then we get another one, except this time instead of getting a USB device interface, we're getting a USB interface. Factory. Again, we have it's versioned, it's all actually not too bad. And then we can open the interface, and then I'm going to gloss over a bit, which is the fact that macOS uses pipe indexes, and you have to work out whether it's the pipe number you actually want, but you just call write pipe and read pipe, and the TO means that you're giving it a timeout. That's all fine. These are all, if you actually go digging through libUSB, you will see all of this code with actual error checking and stuff. So use that code, not my code. So how about Linux? We start with udev. Udev is not too bad. Udev new, udev enumerate new. We're creating an enumerator. We're telling it we want USB devices. We're scanning devices. We get a list. We iterate through the list. We get a name, which gives us a path. And then we create a udev device from that path. And then we get a bunch of things: bus num, dev adder, and sysname. Okay, now what? SNPrintf. So we have to get to the file that contains the descriptors and then read the descriptor in, at which point we can say whether we've got the right vendor and product tuple. SNPrintf. So now we've got the actual device. And at that point, the developers of this gave up on everything being a file and just made you write out big long structures and ioctl it. But now we've got the serial number, so that's okay. And then another ioctl. So that's for claim interface, that's to do the right one. And then read and write is, you guessed it, ioctls. So, yeah. I'm not a fan. Everything is a file mentality that they've used here, I don't think has actually served them well at all. The udev interface was quite nice, but as soon as I had to pivot through SNPrintf using paths that I had to work out myself in order to actually work out where the device was, that didn't really work too well. But this is not the worst USB-related everything is a file API that's around. The USB function FS is used to create user-space devices. So I wanted to test the code that I'd written. That meant I needed a USB device that I had on a stick and could control and control the responses of. Linux has an answer for that. It's called the function FS API. Here's what you need to do. You have to make a magic directory. You have to make more magic directories. You have to echo random values into files that got magically created when you created those magic directories. You have to symlink one of your magic directories to another magic directory. You have to then make another magic directory, mount a magic file system. Then you have to write a bunch of carefully constructed binary data, shove it into a file, which then creates more devices, at which point you can open those devices and start doing stuff with them, at which point you cat a magic value that's dependent on your system into another magic file, and hopefully it connects. My colleague Nigel is here. If you want to say, you can ask him afterwards how much I was swearing as I tried to write this in a way that was repeatable.
I have noise cancelling headphones now. They didn't work.
So, I mean, one could argue that my problems with the Linux USB API are covered off by the fact that everyone uses libUSB. And you can say the same thing about C groups, because C groups has a somewhat alarming file-based API, sorry, and it's also covered by a library, and that's fine. But it's still not, like, it's indicative of a mindset that's gone into this, where we've taken this notion that it's kind of fun when everything's a file, and it worked for /dev, and it kind of worked for /proc, but it sucked. And then we just kept going with it because it was the obvious thing to do. And part of it, I think, is that Unix never really specified how we're supposed to do that kind of thing. It was very concerned with a whole bunch of other stuff, but it never sat down and said, how do you actually configure a system? And so, you know, I think it's just indicative of people get into this railroaded mindset where they just don't think that they could do something another way. But anyway, let's talk about stuff that Unix did standardize. So one of the joke titles for this when I first started writing it was Dave Cutler was right. For those of you who don't know, Dave Cutler was originally with DEC and then went to Microsoft where he created this little operating system called Windows NT. And he was not a fan of Unix, and he was especially not a fan of Unix's I/O model, where he had his joke apparently, where he would say, got a byte, got a byte, got a byte, byte, byte. But anyway, so this is the Unix I/O API, like the guts of it. And this works reasonably well when you think about it running on something like a VAX or a PDP or something like that. You're reading some data in, you're writing some data out. It's really simple, everything's great. Then the internet happened. Or more importantly, people discovered that shoveling data out of sockets and into files and out of files in lots of different ways didn't really work with that API very well because it's blocking. A file descriptor in Unix by default will block. When you read, the read call does not return until it's done its reading. When you write, it doesn't return until it's done its writing. And this slows you down because you can only do one thing at a time. But we have an answer for that, that's fine. We have the most delightfully named system call in the entire Unix pantheon, which I won't pronounce, which we can use to set a flag that says we shouldn't block, at which point we can use the wonderful select API, which showed up in 4.2 BSD in 1983. The problem with this one is that you have to shovel these FD sets, which are effectively large bit strings, 1 bit per file descriptor, into and out of the kernel. And you also have to know how big they are, which kind of limits how many file descriptors you can have. And that's great when you're talking small things, but because, you know, let's not forget, Unix predates the internet. And so, you know, that was okay, but it didn't work too well. AT&T's response was with SVR3 in 1986 was POL. This fixes the file descriptor cap problem, but it means you still have to shovel large amounts of file descriptor records in and out of the kernel and do all that kind of stuff. So it still had performance limitations. And then we had a bit of and then FreeBSD, hi, in 2000 invented this API, which was actually really good. It's a kernel event API. It's not just file descriptor events, it's all kernel events. You can register to listen for any of them and get them all back. That's file descriptor events, file events, like, you know, this file got created, deleted, processes exited, signals happened, all kinds of stuff. And of course, this was really good. It was used to make a whole bunch of nice high performance stuff on FreeBSD. So of course, Linus said, hell no, I'm not taking that. ePOL is okay, I guess, except it's very focused around file descriptors. And so if you want anything else to be an event, you have to create a file descriptor for it because all events are files. No, anyway. But anyway, that's kind of beside the point. Now we have non-blocking IO, and that's great. But the thing is, this IO is still synchronous. Synchronous is different to blocking. Blocking means that you can't do anything else until you finish doing the first thing. Synchronous means you still have to wait for it to finish. It just might finish and say, I couldn't do it right now. And this is really almost tied in with the Unix process model, where a processor's memory is like, it's not strictly sacrosanct, but it's generally not good form for the kernel to go rummaging around in your memory a lot. And asynchrony would require that to be the case. You would have to be able to muck around in the processor's memory and have memory that's shared between two things at once, and that's tricky. It didn't stop POSIX from having a go. Hands up who's actually used this API. Yeah, not many. But on the flip side, that's the Windows equivalent of those calls. But ever since NT 3.5, as in the first release people did it, there's also been these. Those are asynchronous. They have a completion handler. You can do stuff with that. And then WinSock 2 also had similar things. And they also had completion ports. And so that's basically a thing that you listen on, and when your I/O is finished, you get a notice that it happens. And even they have a solution to the I have to open a file descriptor so I can write a byte out to wake my event loop up problem by just posting your own completion event. And I mean, the part of the problem here is that Unix's stuff is all tied to its history. Like, it grew out of systems that were very simple, and Windows does have an unfair advantage here in that it came along both after Unix and after VMS and after a whole bunch of other things where it could learn from it. But my problem with this is not so much that, it's more that we haven't really caught up. When you have a look at what happens under the hood of, like, at the kernel level as opposed to the user level, I/O is really interesting. This is a really bad description of a descriptor ring. Most modern I/O hardware, we're talking SCSI cards or SATA cards, NICs, NVMe, all uses descriptor rings like this in memory. You allocate a block of memory and you carefully misalign one of the lines of that anyway. And each one of those is two 64-byte values, and you generally have a buffer address and some metadata. This varies a lot based on hardware. But once you've got that, you have a host pointer and a device pointer. The host moves through and fills in the buffer addresses, and each buffer address points at some data that might be written out, or an address where the device can write data to. And then as the device sees that those are there, it can move along and fill them in, and then the host can go back and find the ones that are used, and it just loops around at the end and keeps going. If the ring fills up, then you have to wait for stuff to go through. And Linux now has, as of some very short time ago, IOU Ring, which actually does do an I/O API that follows those principles. And I think that's great, but the real issue for me here is that could have happened a long time ago. These hardware descriptor rings have been around for years, but I think there's a combination of, again, just being stuck in the mindset of where we were before, but also just not wanting to rock the boat, and a lot of people thinking at a much higher level these days than the low-level I/O APIs. That means that we don't always take the opportunity to progress these things when we can. But that's sort of at that level. Let's go a level deeper. So I told you I was going for, less controversial. So I want to start this section with a reading from Ian M. Banks's book Accession, in which he describes the concept of an outside context problem. The usual example given to illustrate an outside context problem was imagining you were a tribe on a large fertile island. You'd tamed the land, invented the wheel or writing or whatever. The neighbours were cooperative or enslaved, but at any rate peaceful. And you were busy raising temples to yourself with all the excess productive capacity you had. You're in a position of near absolute power and control which your hallowed ancestors could hardly have dreamed of, and the whole situation was just running along nicely like a canoe on wet grass. When suddenly, this bristling lump of iron appears sailless and trailing steam in the bay, and these guys carrying long, funny-looking sticks come ashore and announce you've just been discovered. You're all subject to the emperor now. He's keen on presents called tax, and these bright-eyed holy men would like a word with your priests. So, obviously, this has a lot to do with C, so now I'm going to talk about farming. Specifically, I'm going to talk about farming in Europe. So, in Europe, they did a lot of farming. They got pretty good at it. And then they got really good at building ships. And so they got on their ships and went out and found that there were other places they could go. And they decided they liked the look of some of those other places, and so they went there. And they got there and they went, right, we're going to farm this place. Good thing there's nobody else here. We'll just do some farming like we did back home. And it didn't work out so well. And it's not because the people weren't there. It's because they had been there for a while. You should read this book. It talks about how the indigenous people of Australia had been farming quite happily until white folks showed up. But the trouble is, it's kind of almost an inversion of this outside context problem, where the outside context doesn't come to the people come to the outside context, and suddenly everything they knew doesn't work anymore. So this is a PDP-11. This is what C was born on. The PDP-11 is a single in-order CPU with a very flat, uncomplicated memory. And when I'm talking like single in-order, I mean like almost like the ridiculously simplified diagram of a CPU that we get occasionally. Like earliest models of PDP-11 didn't even have a clock. When you wanted to read from memory, the CPU would set some address bits, strobe some things, and then the data would come back and it would move on to the next instruction. And so, you know, it's fairly straightforward. It's this very simple lockstep execution thing. There's no cache, there's no memory hierarchy. It's just you read a byte from the memory, and then you might read a byte from an IO device, and then you might add them together, and then you might put them somewhere else. The thing is that time happens, and the PDP-11 begets the VAX, and the VAX influences the 8086, and then a whole bunch of stuff happens, and you end up with an AMD 64 device. And this isn't an AMD 64 device, but this is what a Cortex A77 looks like inside in a very, very simplified form. You will note that this is not a simple in-order CPU with a flat memory hierarchy. You've got instruction decoders, you've got branch predictors, you've got dispatching things, you've got two words that generally show up through sort of the 90s are superscalar and pipelined, and this has both of them in spades. Superscalar refers to the fact that you've got all of these units up the top here that can all do different things at the same time. And then pipelining means that you've got instructions moving at various stages through an execution pipeline at once, and new instructions come into the pipeline as you go through. What does this mean? It means that in order to make C run fast, you have to do things that lie about the underlying execution architecture of what you're actually on. You're not in Europe anymore. And this leads to things like Spectre and Meltdown, because suddenly you're lying about the actual state of the machine in order to make it go fast, but the stuff that you're doing still has ripple effects that go through that can be measured, and that can lead to information that you can get. C is not built to handle this, and a whole bunch of the problem is that we are trying to make a system that looks sufficiently like a PDP-11, but is still really fast, and the things that we do to make it fast make it break. And there are other things that C is not good at. Sorry, let me start that again. There are ways that we could make it better, but they would involve abandoning things that make C C. For example, doing good vectorization means that you can do some kinds of loops really fast. Fortran is really good at this because it knows how big its arrays are, and it has some more guarantees about what things are independent from what other things. And so it can go really fast, which is why Fortran is still used in numerical analysis in ways that C isn't. When you use things like NumPy or Pandas, a lot of the underlying routines that you're using to do that are actually written in Fortran. Another one that gets in the way that C causes problems with is structure layout and padding. C has arcane rules about how structures get laid out and padded. And they cause a whole bunch of problems because you can't then necessarily treat elements in structures as independent variables, which slows things down again. And that's even before you get on to all of the other fun of C. And the real thing is we're just, we're not on a PDP-11 anymore, even as much as we'd like to pretend it. And the core point of this is that C, while it was useful at the time, because when you think about what C came out of, you had to have a very limited language set because it was running on very small computers. It was running on a very simple thing, but we've failed to progress beyond what we could do with that. And it's gotten even worse in this case because we've ended up in this self-reinforcing loop where we make CPUs that are designed to run C fast, which means we can't change C because then we might not be able to do might not be able to write code that goes fast on those CPUs. And to change one involves changing the other. But we do have things that do look different now. We have GPUs, we have things with a lot more vector hardware, and we have languages that are evolving to be able to take use of those. I mean, Rust is an obvious example. I'm not going to tell everyone to go and switch to Rust. I don't even know if Rust is going to be the long-term solution to this, but I think looking at the language and being willing to make changes to it is an important thing. Before I move on, there are two things you should look up here. I've taken a lot of this stuff from a post called C is not a low-level language, which is well worth a read. And a lot of the stuff on farming and colonialism I got from Sarah Tabor, who is well worth a follow on Twitter, and that's her podcast there. But again, I think there are problems that go even deeper. So half the problem with the UNIX philosophy is what even is it? Like, there are a number of different definitions. They all tend to involve a whole bunch of things. I went and actually looked around. There's this one, which I think is the earliest one I found. So making it easy to write, test, and run programs, interactive use instead of batch processing, economy and elegance of design due to size constraints, salvation through suffering. That's very Protestant of them. And self-supporting. And then this sort of evolves into, we start seeing things that we actually more associate with the UNIX philosophy, make each program do one thing well, expect the output of every program to become the input to another, that's your pipelining, so on and so forth. We have Rob Pike's attempt at making it more complicated, I think. And then this is probably the simplest one that I found. Write programs that do one thing and do it well, write programs to work together, write programs to handle text streams because that is universal and everything. Notice that none of those says everything is a file. And in general, I mean, from what the usual sort of surface sort of interpretation of the UNIX philosophy is that you should be able to do this a lot. Or maybe that. But the problem with that is that as a newbie, I don't even know what that means. And then I have to learn regular expressions. And the thing is, like, you often see these things when you're trying to do system administration tasks, which is fine, but if I want to, like, as I do at Yubico a lot, I have to kill my GPG agent because it just gets confused or in the way. And so, I'm going to run PSAOXWW, I'm going to get some things there, and oh crap, I got my grep command as well as GPG agent, so I'm going to have to get rid of grep. And now that I've got that, I have to actually get the PID, so I'm going to have to pipe it through awk or something. And at that point, I can actually kill the damn thing. Now, I'm on a Mac though, so I can hit Command Space and get Spotlight and type a few characters and get effectively the same thing, and then type some stuff in here and then click a button. It's actually quicker, and it's a lot easier to explain to someone than explaining what grep is. And I think the UNIX philosophy, in its expression of doing one thing and doing it well and all that kind of stuff, is a useful starting point, but it really comes into the interpretation of where you're going with that. And I think the trouble that we get is that people get too locked into it. They get too caught up in the purity of it and don't get, and are insufficiently pragmatic and end themselves in knots like the USB function FS interface I showed you before. And Unix is not the only thing to have this kind of a philosophy thing. I mean, the Zen of Python is actually really useful in a bunch of ways. But again, Python, like Unix, has a bunch of things that aren't expressed in the Zen of Python that tend to make life difficult for it. Chris gave a talk at PyCon-AU last year called Fantastic Blocks and Where to Hide Them, where he does talk a bit about Python's philosophical objections to blocks, despite the fact that it has them, it just doesn't know what to do with them. And I think that that's, it's again, getting locked into a particular mindset without actually sort of interrogating it. So the problem with the UNIX philosophy that I have is that the people who tend to express it the most enthusiastically tend to express it in a way that ends up being almost universally user hostile. All of the things that I like about using computers these days tend to be things that violate the UNIX philosophy of doing one thing and doing it well. Because when you abandon that, you can start to glue things together in ways that make things nice and easy to use and quick. I quite like macOS these days. Well, I've liked it for quite a while, and I should have pasted in the XKCD strip of a chart of my satisfaction with how my life is going versus how long since I've opened xorg.conf. Because that's the usual argument that I give to people when they ask why I use a Mac and not FreeBSD or Linux on my desktop. And again, it comes down to getting blinkered about the way that we think and feeling that there is no other way to think. So to finish up, a lot of this has just been me, ranting. It is a beautiful day at the conference, and I am a horrible curmudgeon. But when we get down to it, Unix suited its time. it was the right operating system for the right people at the right time, and then through an accident of bureaucracy, it became the thing that we all use to some extent, greater or lesser. And that's a wonderful thing, but I worry that it has ended up straitjacketing the way that we think, because that time was actually quite a while ago. It still works, which is amazing, but that doesn't mean that its tenets and its way of thought should be sacrosanct. We should feel free to examine every idea and throw them out if we feel that they no longer have value for what we're doing. And that extends beyond things that are purely technical, like Unix. A lot of the ways that our communities got built up over the years, like I remember a time when this was not a dirty word. If it's not a dirty word for you now, it should be. Meritocracy is a lie. But I remember back in the mid to late 90s, almost every community that I was a part of would use this as one of their foundational concepts. We don't see gender, we don't see race, we don't see sexuality, we just see the ability that you have for code. But unexamined underneath that was the reason that you only don't see gender or race or sexuality is that your community is full of straight white men. And as soon as the people who weren't straight white men either showed up or stopped being anonymous figures on the internet and revealed themselves to not be straight white men, suddenly this became a problem. And so you have to then think about what merit actually means. Are these people not showing merit because they're bad, or are they not showing merit because we've set up a systemic structure that stops them from being good or allowing them to be good? And then we try to fix this by bringing in codes of conduct, and the howls and the howls. Because why should I have to be shackled to this code of conduct? Because I've always been a good person, I thought. And that's, that's a problem. And then the other problem that I have is that people like to resort to the pithy philosophical thing, like the Zen of Python is great, but it requires interpretation, as does the UNIX philosophy. And so if anyone comes up to you and tells you that your code of conduct only needs to be excellent to each other, you need to tell them to go away. Because unspoken beneath this is, who must be excellent to whom? If I bait you by calling you slurs or something like that until you explode at me in a fit of rage that I have quite rightly earned, have you been excellent to me? And at that point, can I run to my governing body and say, oh, they yelled at me, kick them out? And conduct and community management requires a lot more sensitivity and a lot more nuance than that. And so in both community and technical sense, it's safe to say that complex problems have simple, easy to understand, wrong answers. And that we should understand the past because it's important to know it so you can learn from it, but you can't let it bind the future because that just closes things off. As Sean Brady said in his keynote yesterday, it's important to learn that sometimes you can drop your tools and try and make new ones. And thank you very much. If anyone does want to tell me, come and talk to me, feel free to find me out there. I will say, though, that if you want to lecture me and tell me I'm wrong, you have to buy me a drink first.
Well, thank you very much. We've got a small gift, a token of our appreciation. We do have a few more minutes to go. It's not actually time up yet. So if you do want to have a question, just put your hand up and I'll bring you the microphone. No? Jammed up at the door, mate. Thank you very much.
Thank you very much.
Okay.